What's up guys, it's me Sir Ernest, and today we will finish our discussion on the motion of particles in a rotating coordinate system. So let's have a brief recall of what we've discussed so far. So here we consider the particle that is represented by two coordinate systems. One is fixed and one is rotating. So the I, j, and k hat component unit vectors refer to the unit vectors in the fixed frame, and the ones with the prime refers to your unit vectors in the rotating frame. So when we calculated the velocity of a particle, the velocity of a particle with respect to the fixed frame is now equal to the velocity of your particle with respect to the rotating frame plus a velocity term due to the rotation of your coordinate system represented by your omega. So this is omega cross r prime, where r prime is the position of your particle with respect to your moving frame. Okay, and from here we concluded that we can apply this result and generalize it by this equation, wherein the operation of differentiating any vector q with respect to time in the fixed frame, that is equivalent to the differentiation of that same vector with respect to time in the rotating frame plus the operation omega cross on that vector. Okay, so for instance, we apply that to let's say to the velocity vector. Okay, so let's say suppose your velocity vector is your q. So applying this, that result, we have derivative of v with respect to time in the fixed frame is equal to the derivative of the velocity with respect to time in the rotating frame plus omega cross v. Because remember that v is equal to v prime plus omega cross r prime, then we have this expression, the derivative with respect to time in the rotating frame, and this is applied to v prime plus omega cross r prime plus omega cross v prime plus omega cross r prime. So this one we can separate this. So this derivative of v prime with respect to time in the rotating frame plus derivative with respect to time of omega cross r prime, again in the rotating frame, plus omega cross v prime plus omega cross r prime, and this is equal to what? This is equal to derivative v prime with respect to time the rotating frame plus, here we're going to apply chain rule. So this is derivative of omega with respect to time in the rotating frame cross r prime. Remember, when you're dealing with the vector product or cross product, the order should matter, or the order should be maintained. Okay, so the second term would be omega cross derivative of r prime with respect to time in the rotating frame. plus this one and this one. Okay, now let's look at these derivatives. This derivative is just the derivative of velocity with respect to time with the rotating frame. So this is the acceleration in the rotating frame. This is the acceleration in the fixed frame. Sorry, no prime. Okay. How about this one? This one, omega with respect to time in the rotating frame. So let's look at this. Okay. Let's write it here. Okay. So derivative of omega with respect to time in the fixed frame. So here we are going to set q to be omega. This is equal to derivative of omega with respect to time in the rotating frame plus omega cross omega. Okay, so we take the cross product of a vector with itself. This is what? Correct, this is 0. Okay, so this means that this is equal to omega dot. So this term is just the time derivative of omega with respect to time. Okay, this term is the derivative of position with respect to time in the rotating frame. So this is the velocity of your particle in the rotating frame. So from here we can rewrite this as, or summarize this as follows. So this is A equals A prime. This is A prime. This is the acceleration of your particle with respect to the moving frame. Plus, this is omega dot cross r prime plus omega cross v prime plus omega cross v prime plus omega cross r prime. So it's remember here that we maintain the order of cross product. We take the cross product between omega and r prime first before taking the cross product of that vector with omega prime, with omega. These are the same. So the final expression would be A equals A prime plus omega dot cross r prime plus 2 omega cross v prime plus omega cross r prime. So this expression provides us the acceleration in the fixed frame in terms of the position, velocity, and acceleration of your particle in the rotating frame. Of course, we are also considering the rotational velocity or the angular velocity of the moving frame. Okay, so in the next video we're going to generalize this with the with translational acceleration, wherein we're going to consider that for a general case of a non-inertial reference frame wherein the moving frame is both rotating and translating at the same time. Okay, so for now, that's all, and I hope you learned something today. That ends our discussion on the motion of particles in a purely rotating coordinate system. Thank you guys for watching, and I'll see you guys in the next video. Bye bye.